Good afternoon. Oh, it's not coming up. Yeah. So I'd like to start by thanking Aegis and all the organizers for the invitation to be here today. It's a nice pleasure to come back to the Institute. I was here in the first group who came from Brasilia to start this place, so it's always a great pleasure to come back. In a way, it's kind of coming back home, because I lived here for a little while. And also, I would like to make a disclaimer, because my talk is not about quantum magnonics at all. And I talked to Aegis about this, and he assured me that it should be okay. And so there will be quantum, there will be 2 slides about magnons, but not quantum magnonics per se. But I hope it will come as a little bit of, at least I hope it will be sufficiently entertaining for you, and being the last talk of the day, and I know you're tired, maybe it's a relief to go off topic a little bit. So I'll talk about this idea of engineering a nodal line semi-metal using vacancies in a crystalline structure, and how can that system or this phase can be turned into a magnetic insulator using electron-electron interactions. And the heavy lift of this work was carried out by my collaborators from Rio de Janeiro, and here the guy who did most of the analytical work for the quantum phase transition to the magnetic phase is sitting over there. Don't try to hide, because the questions will be directed to you when it comes to part of this work, at least. Yeah, so without further ado, so I would like to give a little bit of background, because I'm not sure how many of you have heard about this stuff that I'll be talking about. So I'll briefly introduce what these non-symmorphic symmetries are, and I'll just make a very brief overview on topological semi-metals. And then the bottom line is that I can engineer nodal line semi-metals using vacancies, as I have already told you. And I'll show you how this actually works in real materials, like, for example, graphene and boraphene, using density functional theory. But then, as soon as we introduce electron, this is for non-interacting, without electron-electron interactions, but if we put on electron-electron interactions in your material, or consider the role of electron-electron interactions, then you want to ask the question, what happens with this nodal line semi-metal? And so we investigated this question for the 3 regimes of electron-electron interactions: weakly, strongly, and intermediately interacting regimes. In this case, we carried out this case study for graphene, and I'll show you some of our results, preliminary results. So the motivation is that, just look at this picture of magnetization as a function of the strength of U, which is the electron-electron interaction, and this green symbols here represent the phase transition of pristine graphene. So this result is known that about 3.8 U in units of T is the hopping amplitude in your pristine graphene. You get a phase transition from a non-magnetic system to a magnetic system with a finite magnetization, but it takes a rather strong electron-electron interaction for this to occur in your pristine graphene. And I want to understand what happens if I take out some of these carbon atoms in a certain way, and what happens with this phase transition. Does this point, where does it go, and if there will be a phase transition at all? And okay, so this all starts with this notion of non-symmorphic symmetry. So in 2 dimensions, so I'm talking about 2-dimensional materials, we have just 17 crystalline crystallographic groups. So they are represented here by these nice wallpaper patterns. and these are actually called wallpaper groups, because all of them can actually have an analogy with tiles or tapestry, stuff like that. And so out of the 17 groups, and these groups are classified according to these symmetries, translations, rotations, reflections, and in 2 dimensions, you have just one type of non-symmetric symmetry, which is the glide plane or glide line, instead of, as opposed to 3 dimensions where you have also a screw axis. But a non-symmetric symmetry is basically any symmetry that involves a fractional translation of the unit cell of your crystal. So you reflect, but you shift a little bit, or you rotate, but then you have to shift a little bit, a fraction of the unit cell. Then that's what a non-symmetric symmetry, crystalline symmetry is. So in 2 dimensions, only 4 of the 17 groups are non-symmetric. These are highlighted here. Some other types of non-symmetric patterns are highlighted here for your amusement. But let's now, how does that connect with topological semimetals? So what are topological semimetals? These are crystals where the conduction band and the valence band, they touch at points or only at points or along lines in the brilliant zone. And then you have the well-known Dirac semimetal. So graphene is a Dirac semimetal. We have the 3-dimensional vial semimetals, where you have these 2 time reversed related band touching points. Here, and they have monopoles, which are topological charges that are attached to these points and make them topological semimetals. And then we have also topological nodal line semimetals, where the bands touch, or rather cross along lines in the brilliant zone. And these are rather interesting for various reasons, because they are home for different novel topological phenomena, superconductivity, and non-trivial magnetism as well. And the thing with a nodal line, or any band degeneracy for that matter, is that one of 2 things can happen if you put in perturbations in your system, right? So either the perturbations will split up the band degeneracies or not. So in the first case, this band degeneracies here, a nodal line, is called accidental, because if it only exists, the band degeneracy only exists within a regime of parameters. So if you perturb your Hamiltonian or your structure microscopic parameters, then you split up the bands. This is a general result of energy level repulsion. We know that. So this accidental, they are not very useful for applications, for example, because they're very fragile, these band degeneracies, and they are normally associated to symmetric symmetries, more often combined with non-spatial symmetries like chiral particle whole time reversal. But sometimes the band degeneracy, the nodal line in this case, is symmetry enforced. And this is the case that emerges when you have non-symmetric spatial symmetries in your material. So the question is, how do I get these non-symmetric materials? So there are, the non-symmetric space groups, and here are some examples of materials that fall into this generic class of non-symmetric materials. Point is, they're very often, more often than not, very chemically and structurally costly and kind of cumbersome. But what I'm offering is an alternative rule to get a very boring, in principle, in terms of structure and chemical composition material, even monotonic and structurally simple, 2-dimensional, and I don't have time to go into this, but nodal line semimetals are not even expected to exist in 2 spatial dimensions, but this route gives it for other fundamental reasons. But so the point here is that you can make it non-symmetric by poking holes in it, by introducing vacancies in some clever way. And this is a bunch of a few papers that we published, that I published with some other co-authors that explore just this fundamental question. So let me just acknowledge them very quickly here. And what we found is that, say you start with a pristine borophyne. Borophyne is just like graphene. Instead of carbon, you have boron atoms. And you have a boron atom at the center of the hexagons here. And graphene, you know, you just have the hexagon structure. But here you have an extra atom in the middle of the hexagon. So both of from a symmetry point of view, these systems, they are completely equivalent. They have two reflection planes which are perpendicular to each other and an inversion point. And that's basically what gives rise to the Dirac cone, which, as I have told you, is fragile to perturbations, specifically to spin-orbit coupling. And that's an important point for applications, for example, because you want to use these materials in some kind of proximity ties with spin-orbit coupled materials. And so, okay, so but this Dirac cone is very fragile to perturbation in general and spin-orbit coupling in particular. But if you just remove atoms in a certain way, so you trade one of the reflection planes by with a glide plane, and then instead of a Dirac cone, you get this nodal line, and also it's very robust. Actually, it's symmetry enforced, so it's arbitrarily robust to perturbations. So let me show you this, how this works analytically with a very simple-minded model that I used to model this real structure. So let's say we get this borophyne with vacancies which are distributed in this way. So the minimal model for this actual structure is a model that has a unit cell of 4 points which are shifted in this way. And that's basically what's giving me the glide plane, which is here depicted in purple. And this can be effectively written as a 4x4 Hamiltonian, which I am writing down here. And then I just start giving entries which are completely generic, just hopping. And I'm not assuming anything about the values of this hopping. So these are the intracell hoppings, intercell hopping in horizontal direction, vertical direction, and diagonal direction. But I'm not saying anything about what are the values of these parameters. And then I just enforce these three symmetries onto this Hamiltonian: glide plane, inversion point, and time reversal symmetry. And these are the invariance relations which this matrix has to satisfy in order for it to be glide symmetric, inversion symmetric, and time reversal symmetric. And for that particular lattice, I can write down all these 4 matrices, and they are given here just for you to know that we can write down the matrices, so and so. And then we plug everything together, and I get the constraints on this so far generic numbers. And then when I plot the band structure for this 4x4 Hamiltonian, what I get is that first, if I just impose glide plane, I get that the bands necessarily have to touch at ky equals 0 and ky equals pi or minus pi, because these are the high symmetry points in the Brillouin zone for that Hamiltonian. And these are the band touching points projected on the kx, ky Brillouin zone. And the bands have to touch pairwise. So if I would have 6 bands, then I would have 3 band touching points along each one of these lines. So now if I impose inversion point, then what happens is that these band touching points are pushed, all of them, to kx equals pi. Now time reversal symmetry comes along, and what it does is that it connects these points along the kx equals pi direction in my Brillouin zone. And also, not important for my argument today, but for applications sometimes, it also induces an accidental nodal line at ky equals 0 here. And in fact, if I play with anisotropy in that toy model by like changing the values of my hoppings a little bit, so if I introduce some level of anisotropy, I can prove that this accidental nodal line can be moved inwards in the brilliant zone, and the shape of that nodal line, accidental nodal line, can be deformed at will, but the symmetry-enforced nodal lines are, because they are symmetry-enforced, they are fixed at the symmetry, the high symmetry kx equal pi in line in the brilliant zone, and yeah, so they can't move. So, and they can't actually be gapped out. These purple lines can eventually be gapped out by if the anisotropy is too strong, but not those symmetry-enforced nodal lines. So the DFT results for Borofin confirm this analytical prediction. So here I'm just showing you showing results for two types of vacancy engineered borofins with 10 atoms in the unit cell, 16 atoms. And you see that at kx equals pi over AA, here is the lattice spacing, but the point is that at kx equals plus or minus pi in units of the lattice spacing, you have the nodal line in both cases, and then you have these accidental nodal lines inside the brilliant zone that come from anisotropy. And we carry on a robustness test on these nodal lines, and then we see that if we include spin-orbit coupling as strong in this material as 0.1 electron volts, the nodal lines which are accidental inside the brilliant zone, the degeneracy gets split because of spin-orbit coupling, but not here at the edges of the brilliant zone where the nodal lines are symmetry-enforced. Eventually, these nodal lines inside the brilliant zone will be gapped out by strong enough spin-orbit coupling. What we found here, which is interesting, is that this is really huge for borofin or graphene. So we just did it as a test, but this is above nowadays capability of inducing spin-orbit coupling with electric field in such materials because these atoms are so light. But just to understand that this, although accidental, these nodal lines are still very robust if you could actually crank spin-orbit coupling all the way up to 0.1 electron volts in such materials, the nodal lines still be there. So which is kind of unusual level of robustness for accidental nodal lines, and we attributed this to the origin of these nodal lines being anisotropy, because this is also a structural fact. So spin-orbit coupling won't make the material more isotropic. So yeah, so this was actually a long parenthesis. So also for graphene, we see that the nodal lines, the symmetry-enforced nodal lines appear where they should. So here it's an interesting structure because we have two orthogonal glide planes. So you have a symmetry-enforced nodal line all around the brilliant zone. And here you have just at this ky equals pi or minus pi edges. Here inside, again, the accidental nodal lines. And now coming to the magnetic part of my topic, of my talk. So we want to explore magnetism in such nodal line semi-metals. So we investigate this Hamiltonian with where U here is the strength of electron-electron interaction. So here you have the typical Hubbard electron-electron interaction term. And the symmetry is encoded in the equalities between the hoppings for neighboring sites like so and so. And then but before, we just want to calculate the spectral functions and local density of states for the non-interact. So U equals 0. Just compute local density of states for this structure. And we found that, well, these are results. I don't want to go into the details, but only want to mention that, well, first of all, the local density of states depends on where you are. So it depends on the coordination number of the site. This is not absurdly surprising because you have this anisotropy in your system. So the local density of states will see that. So it depends, it's non-uniform. But what is interesting is that you have a Van Hove singularity at 0 energy, whereas in pristine graphene, we get a vanishing density of states at 0 energy. And here we have a peak at the local density of states at 0 energy, but sometimes not, depending on, again, where you are in your structure. So here, 4 and 9 means these sites on the unit cell. So this Van Hove singularity at 0 energy is telling us that, okay, you really have a good chance that you have instabilities at the Fermi level that could drive a phase transition to a strongly correlated phase. So then putting back in U and doing first mean field theory, considering the weakly interacting regime for small values of U, we get the mean field Hamiltonian, as you guys know. This is the version that comes out from the Hubbard model. Here is the magnetic order parameter. And the calculations of the free energy from which we take the magnetic order parameter by minimizing the free energy will give us the following picture. So if we plot magnetization or the magnetic order parameter as a function of the electronic interaction, we get, first of all, non-uniform magnetization. So it depends on where you're sitting in your unit cell. The magnetization is different. And it's in fact weaker at the sites which are more coordinated, that has a larger number of bonds. And the interesting thing is that graphene, pristine graphene, as I showed you before, as the bottom line motivation, has a critical U in units of hopping that's known to be around 3.8. And here you're seeing that as U goes down all the way to zero, you always have some magnetization. So apparently in this mean field theory, we are getting that the system magnetizes for arbitrarily weak electron-electron interaction. And then we go to the opposite regime in terms of electron-electron interaction. And for that we use linear spin wave theory. Rodrigo did this calculation, and he told us that in this regime, the Hubbard Hamiltonian can be mapped onto the Heisenberg Hamiltonian. And then we use Holstein-Primakov linearization, get this linearized version of your Hamiltonian in the first approximation, and then we just have this matrix, which is your Bloch matrix for your magnons in this strongly interacting regime of graphene, of this vacancy engineered graphene. And then, so you diagonalize this matrix, and you get these magnon bands, which for this material will look like this. And the point here that I just want to comment on is that this lowest band is gapless at the gamma point, which points towards the existence of these Goldstone modes, which are associated to zero mass Goldstone modes, which are associated with breaking SU2 symmetry, therefore like spontaneous magnetization. So just confirming what we have already obtained from mean field theory, but now in the opposite regime of electron-electron interactions. We can also compute the magnetic order parameter in this regime by using the quantum correction to the magnetization like this, using this Q matrix that's coming from the diagonalization of the Hamiltonian. And this gives us the magnetization, and we compute magnetization, and again we see that the magnetization is non-uniform, and again it's weaker at the sites which are the larger coordination site, larger coordinated sites. And if we compute the average magnetization, in this case, we get some number which is smaller than what we get in pristine graphene. So what was kind of the picture that is building up is that we get magnetization for arbitrarily weak electron-electron interactions, but when the interactions are very strong, then the net magnetization in this depleted lattice is actually smaller than the one that is known for pristine graphene. So now going to the intermediate value of interactions, we use quantum Monte Carlo simulations to get the magnetic order parameter and correlations. And here are the results: magnetic order parameter and correlations as a function of electron-electron interactions. And the take-home lessons lesson from these plots is that, again, the magnetization is weaker, and also the spin correlation is weaker at the sites with larger coordination numbers. So this magnetization is highly non-uniform in the material, which is different from what we get in pristine graphene. So correlation as a function of distance. So what we get is that this upper picture here shows that for U is smaller than the critical value of pristine graphene. The depleted lattice, which is the purple result here, shows a much stronger correlation than pristine graphene, which is the honeycomb lattice here. But if you go to the regime where the U is larger than the critical value for pristine graphene, they become comparable. So we are basically coming up to the conclusion that vacancy, when you do this vacancy engineering, you're inducing stronger spin correlations at much weaker strengths of the electronic interactions than you need in pristine graphene. Let's see. So we can also, using quantum Monte Carlo, carry on calculations for the spin structure factor, antiferromagnetic in this case. And so here are the results, but I think that I might be running out of time. I just want to point out to the fact that if we extrapolate to the thermodynamic limit, where n is the number of sites, really large, then we still have a non-zero net magnetization here. This is whereas in pristine graphene it always goes to zero, right? So we have this magnetic order remaining in the thermodynamic limit when U is as low as 2.5. Here the lowest value of the simulations was 2.5, right? So it's the lowest lying extrapolation here in the thermodynamic limit. So we can also compute the So when we put this together, like magnetization versus U, so here is the result for pristine graphene that I have already commented at the beginning, and this is the result for our depleted honeycomb lattice. So you see that you have this tail here going all the way to small u, and also what's interesting is that the saturation value for the depleted lattice is attained for much lower values of U, but at the end this value is lower than the saturation value of pristine graphene, which takes a much larger U to be attained. So we can use, again, quantum Monte Carlo to compute electronic compressibility. And basically here, the information that is acquired is that the compressibility goes to 0 as U increases at low temperature. So for temperatures which are low enough, as you increase U, the compressibility goes to 0, and this is the signature of the emergence of an insulating phase. So I started with a nodal semi-metal that it's becoming an insulator, a magnetic insulator due to strong or not so strong electron-electron interactions. That's an interesting feature of this material. And then if we put all this together in this plane, temperature versus electron-electron interactions, we see that actually the magnetic transition, which is here given by this line, and this metal insulator transition that comes from the compressibility, the analysis of the compressibility, they basically coincide. They're very close. So, which indicate that in fact you have, this is the critical line that determines the transition between a non-magnetic nodal line semi-metal for low enough U and high enough T to an antiferromagnetic Mott insulator where you have this opening of insulating gap from interactions, although your band structure is that of a nodal line semi-metal. So that's the phase diagram that we can extract from this investigation. And I think with that I can come to my conclusions that I showed you that I can obtain a symmetry-enforced nodal line semi-metal, and by that I mean it's robust to arbitrarily strong interactions that preserve the symmetries that enforce the phase in the to start with. And this can be done using vacancy engineering in a two-dimensional, even monatomic structure. And that this kind of material will host Van Hove singularities at 0 energy that will tell you that you have a very good chance to develop a strongly correlated phase with interactions, and that's the question that we wanted to explore. And using mean field theory, linear spin wave theory, and quantum Monte Carlo, we do predict that this phase transition to a strongly correlated phase occur, and this is an insulating antiferromagnetic phase. And this happens at very weak. Actually, our results indicate that arbitrarily weak electron-electron interactions, which are non-zero. In this, that we carried out for vacancy engineered graphene, and because we know the result for pristine graphene to the critical point to be 3.8. So we wanted to compare with something that we already knew from the literature. However, this scheme is based solely on symmetries, which means that it doesn't have to be graphene. It just have to start with this vacancy engineered nodal line semi-metal and repeat the procedure. So the methodology and the fundamental physics does not rely on chemical composition or the microscopic details of the materials at all. So yeah, so I'm telling you that you can engineer a robust nodal line semi-metal simply by poking holes in a monoatomic symorphic crystal, and this is a path for phase transitions to correlated phases of matter because of, for one, the Van Hove singularity of at zero energy. And well, this is mainly my tools of work, my work tools, the pencil and the rubber, and here poking holes is the method for getting interesting physics and phenomena and phases. More often the razor than the pencil is used, but still can give interesting, very fundamental phenomena that maybe lead to applications. Thank you very much for your attention.
Thank you, Mariana. Dennis, then Yaroslav.
Thanks a lot, Mariana. I have two questions, if Carlos allows. The first one is, what is the, not implantation, because you're not implanting anything, but what is the experimental precision, spatial precision for removing like these atoms, kicking them out and creating like vacancies?
No,
like in
I
a
don't
real
think you can actually remove. You have to grow it like that, because if you want to remove, you don't have this type of precision. Because if you want to remove, like using helium beam or something, you will make you can create vacancies, but randomly distributed and of random sizes. And I need these vacancies to be part of the crystalline structure. And as a matter of fact, they have to be distributed periodically, so that the bottom line, you're trading this a reflection plane with a glide symmetry, with a glide plane, like here, for example.
Right. So I think to rephrase my question, is this like experimentally realizable?
Yeah.
People have already
So
started
this
looking at
this guys this
well, this one,
no,
yes,
for borophene,
yeah.
there's a class of materials called beta borophines. So they are like this is the borophene without vacancies, and they can create these vacancies which are periodically distributed, but like for different types of unit cells. Not only this, but a class of these beta borophines. So this is realizable. The thing is that they were not thinking about symmetries specifically, so I need these vacancies to be distributed in such a way that it gives me this glide plane. And this I'm not so sure whether, I mean, in principle, it's the same experimental mechanism.
So the other question that I had, one more, thank you. The other question that I had regards for instance, if we think about like a graphene pristine, and we terminate either zigzag or armchair, there's going to be like add states at zero energy. So I'm just like wondering whether this like Van Hoff like singularities that you got at energy equals to zero arises because when you introduce like these defects, it's almost like introducing a line defect in your sample. And yeah.
Yeah, it's a good analogy. But I think fundamentally the physics a bit different, because I didn't show this in my talk, but we found that these Van Hoff singularities come from this point where the accidental nodal line touches, or actually this point where the symmetry-enforced nodal lines and the accidental nodal line here touch. And well, but then you can say, but these nodal lines are coming from these line defects, and that's true. But I think that it's a bit different from a fundamental perspective.
Thank you.
Okay. So yeah, I have this. So, thank you for the talk. I also have two short questions. One is I'm confused because you first derived, well, okay, in your toy model, but doesn't matter, this nodal line using inversion symmetry, and then on this slide, well, on another slide, you argue that if the inversion symmetry is gone, if you add spin-orbit, which breaks the inversion symmetry, the nodal line is still there. I would actually expect the opposite because you have just broken the symmetry.
But what do you mean?
Well, you have spin-orbit interaction only if the inversion symmetry is broken.
No, but not in the material. Like, you mean because you apply some electric field and you break inversion symmetry, but the material is two-dimensional.
Yeah, it could be intrinsic, could be extrinsic. I mean, everything gives spin-orbit.
Yeah, well, I'm not sure I get this because, well, so let's go back a little bit. So it's true that inversion symmetry pushes these points which are actually generated by the glide symmetry. So these are the 2 points which are enforced by glide symmetry, and inversion symmetry, the job of inversion symmetry to push these 2 points to this to kx equals pi here. So I'm not sure that it's tremendously relevant for the nodal line, but maybe the nodal line will be distorted because of if you don't get the inversion symmetry. But even though I'm not so sure, because I think that okay, so let me state that this is Rashba spin-orbit coupling. So I think you're talking about the breaking inversion symmetry out of the plane of the material, right? But
Yeah, it doesn't matter. Rashba also breaks inversion, right? So if you change p to minus p, you have to change sigma to minus sigma.
Mm.
Did your analysis take care of the double group, including spin, or was it just without spin in the previous slide?
No, in the previous, it's spinless.
Yeah.
The toy model is spinless.
Yeah. So in the next slide, you have time reversal you have to worry about instead of inversion.
Yeah, I think so.
Yeah.
Yeah, but then, time reversal here is also, but the spin orbit coupling doesn't break time reversal symmetry.
No.
So
It doesn't.
I think.
Okay, maybe let me ask another one, the most likely question that none of us know, answer that none of us knows. But for example, if you take zigzag antiferromagnet, we know that the spectrum of magnons, spin waves, has a nodal line.
The spectrum of magnons. Okay.
Spectrum of magnets, yes. Now, of course, you are not doing that, but at some point, at strong coupling, you have a mapping. I thought maybe in one of the limiting cases of your mapping, you get something like that. No.
This is not a question that even crossed our minds, but it's a very interesting one.
Okay. Good. Thank you.
Thank you.
Okay, so I had a question about, you did the mean field analysis with the U, and I think you decoupled it in the spin density wave channel. But I was wondering, is it possible that you could you could have instability in different channels? And if so, like charge density wave or something, like if you can have different types of instabilities, and if so, how would the picture change?
Yeah. So you're talking about this part, right?
Yeah, you're doing the mean field analysis. You're decoupling it
mean
in the
field
spin
is-
density wave channel, but there's other channels in principle that can have instabilities. So if you include the other channels,
Which channels?
like charge density wave or something like that, like can you have instabilities in other channels? And if so, how would that change this picture?
Yeah. So we didn't look at that. So we just looked for the spin channel, and did so mean field and in the weakly interacting regime, just considering the magnetic order parameter and looked at what happened with it, but not for the charge density order parameter. Because we wanted to compare with pristine graphene, where the magnetic picture is well established. Yeah, could be. Yeah.
One more question. Oh, sorry. So you mentioned that this is material independent.
Yeah.
And I remember that in the beginning you showed like some slides. You had like a slide where you applied like different symmetry operations into your Hamiltonian, and yeah, exactly, this is slide. So, but if you go like forward, just to see the right, yeah, exactly. But as far as I understood, this the energy at equals to 0, this is kind of like generally material independent, but you need to have these matrices to ensure the nodal line at energy equals to 0.
Well, you can always have these matrices.
Well-
These are just the transformations.
Right, but
But
that
then,
and-
what I'm enforcing is that these transformations are symmetries.
right, but that depends on, like, for instance, the orbitals of your atoms. So depending on which orbital you have, transforming the Hamiltonian with respect to inversion, symmetry, or gliding plane might change. So namely, the formal structure of the symmetry might
Yeah.
depend on the orbital you are considering. So I just wanted to know whether you could comment on the influence on the shapes, or what are the orbitals that give rise to.
Yeah.
Yeah, because I'm not sure. Well, I think I just wanted to push back a little bit on this, like, material
On the
independent
claim,
thing.
yeah.
Just because I agree that for that form of the symmetries, you're always going to have that, but that form of the symmetries, it's going to depend ultimately on the orbitals of
Oh
the
yeah.
atoms.
Yeah. If you have like this is a. Notice that I'm quoting this as a minimal model because that's actually what it is. It's a minimal model, but in your actual material, your unit cell has much more than just 4 points, and has orbitals and spin, and so on. So your matrices are going to be much larger than that, and more complex. But what I'm saying is that if you have these symmetries, whatever more complicated matrix you have, and Hamiltonian, because you have a much larger unit cell, then what I'm telling you is that I guarantee this to give you this symmetry-enforced nodal lines. Actually, I'm telling you a bit more because of these accidental nodal lines, which are actually more robust than they should be, but this is a bit off topic. But I want to focus on the symmetry-enforced nodal lines. So.
Thank you.
Okay, I guess this is a good time for us to break away and stop for the day. I would like to thank you all for the nice discussion. Thank you, Mariana, again. But before we just leave, let me make sure you all know where to eat tonight. So there are plenty of restaurants in Ponta Negra. I can write down a couple of more well-known ones if you want, say, steaks or seafood. There are many. We could probably meet maybe later in the lobby around 7:30.